In the case of animal ethics, it's all but considered poor form to rate consciousness above the sacred status of intelligence. But this sleight of hand, this declaration of a natural hierarchy, is precisely what hides the troubling truth, that it is we, the intelligent, who dictate the standards of a humane act. In industry, the deciding factor that tends to save species from the chopping block is a display of sapience over sentience. As a class, sentience can be reflected by little more than a basic show of conscious awareness, such as a response to pain. But sapience goes one step further, adding to its awareness a level of subjectivity, an awareness of the awareness, so to speak. So whereas a mouse may respond to the sensations of pleasure and pain, it does not appear to think of itself as an individual. This trait is more often attributed to animals who creatively cooperate, empathise, or, as mentioned earlier, recognise themselves in a mirror. Animals like apes, elephants, whales, or dolphins. In fact, it's such a high cognitive benchmark that it usually takes 18 months to show in humans. But though the realm of sapience may be slim, the mouth-watering realm of sentience is vast and broad. As said, if any entity can show either an intent towards or away from something that affects its survival, it could arguably be attributed with a basal notion of consciousness. But when does the ability to react to stimuli become an experience of pleasure or pain? When do we define a living thing as sentient? And are these the ultimate borders of consciousness? Good morrow, fellow humans. My name is Sean and I am obsessed with infinity. So join me as I attempt to unpick the infinities of what is. Carl Jung once wrote, "Just as the human body represents a whole museum of organs, each with a long evolutionary history behind it, so we should expect to find that the mind is organised in a similar way. It can no more be a product without history than is the body in which it exists." So, what is this history? Though Jung may have been referring to the more recent evolution of a psychological mind, what is its genesis? Well, again, according to The Intelligent Ape, the Great Divide is thought to be yet another aspect of natural hierarchy. In this case, the inheritance or lack of a central nervous system. Approximately 1.547 billion years ago, the lineage of animals split from the plants. 9 million years later, our cousins, the fungi, also took up their own branch. Though the complex nervous system would not be present for another billion years. After our previous chapter's inquiry into the mind, you would be forgiven for thinking that the brain stands alone as the seat of our conscious awareness. But when we inquire into this same story via the lens of evolution, what presents itself is a tale of how the brain came to be the subservient partner of what was an already successful nervous system, and not the other way around. All of us know that a brain is fundamentally a collective of neurons and synapses, though it would be wrong for us to think that neurons are particular to the brain. By entwining the central nervous system into the peripheral system, the part of the body responsible for acquiring sensory information, neurons operate throughout the body. Of course, much of this information is then regularly forwarded up to the brain. Still, it could just as easily be sent directly to the motor neurons, as in the case of reflex actions, which not only bypass our subjective awareness, but bypass the brain entirely. And so what becomes clear is that the body and brain are more akin to a unified organ, a single system that can enact a wide variety of actions without either sentient or sapient intervention. Indeed, apart from certain genomic variations, neurons are vastly the same as any other somatic cell, differing primarily in only structure and function. Be it a neuron, a blood cell, a fat cell, a cardiac cell, or any other, each are made of the same organic molecules. The point being that a neuron is not a unique substance, it's a behaviour. As has been highlighted across our prior investigations, systems are rarely material in their fundamental structure. Rather, these systems are an emergent scaffolding of emergent relationships. The nervous system is merely an abstracted whole, justified by a scaffolding of many other abstracted wholes, all of which are, in actuality, one continuous, single stream of related behaviour. And this is an idea that I'd like you to hold on to as we continue to unfold our thinking. Irrespective of this, however, the evolutionary sciences remain confident that, though gradual and continuous, the emergence of sapience, sentience, and so perhaps even consciousness can be aligned to three distinct evolutionary stages. The first was when single-celled organisms acquired the ability to respond to stimuli. The second was when they began to centralize their information processing into those earlier distributed nervous systems. And the third was when this same centralizing characteristic led to the evolution of primitive brains. For the material-minded biologist or neurophysicist, the difference between a complex central nervous system like our own and a more ancient distributed nervous system like that of the jellyfish or coral is indicative of this very divide between sentience and non-sentience. Similarly to the abstracted divide between our own non-conscious peripheral system and our sapience justifying central nervous system, the distributed nervous system is thought to be incapable of sentience. But again, is this the ultimate border of consciousness we have been seeking? How could we be so sure that the lines are that easily drawn? Today, the species that offer us our best insight into this crucible event are the porifera, placozoans, cnidarians, and ctenophores. Yeah, I agree. These animals aren't likely to be seen representing the letter C or P in children's books anytime soon, though they may not seem too unfamiliar once their family members have been introduced. The porifera, which includes the sponges, were first recognised as animals in 1866 by biologist Henry James Clark, and due to their lack of neurons, have long been thought to sit on the lowest branches of Animalia evolution. But though they lack those vital neurons, they do, however, host a tangle of proteins that look very much predestined to become a nervous system. In fact, at the atomic scale, they can be as much as 90% genetically similar to the proteins that form neurotransmitters in us. Why sponges don't have a nervous system, and yet do host these synaptic-forming proteins, is not currently understood. However, there are two schools of thought on the matter. Initially, as it was assumed that sponges were among the earliest incarnations of Animalia, it was then sensibly concluded that the species must have separated from the primary animal branch prior to the evolution of the nervous system. In such a case, the appearance of these proteins is explained as an example of exaptation, where one evolutionary system becomes repurposed. In much the same way that the feather, having evolved for temperature regulation in dinosaurs, later became the bird's key to flight. Or how the human hand, evolved for grasping tree branches, later became our ability to send text messages. The alternative to this hypothesis is that the porifera and placozoa once had elementary nervous systems but lost them in a case of degenerative evolution, akin to when flightless birds lost their ability to fly, or when we lost our tree climbing abilities to thumb off the odd emoji. First discovered in the 1880s on the glass walls of aquariums, the placozoans are another extremely simple multicellular organism. Flat and only 1 millimetre in diameter, each host a minuscule 6 cell types, none of which show any relation to the neuron. That said, they do, like the sponges, showcase many of the genes necessary for neuronal development. This genomic similarity is why placozoa cells are currently considered the evolutionary precursor of the classical neuron. But what's intriguing for us is that they can still show signs of complex behaviour, changing speed in reaction to food, or even preference for environments. They can even right themselves when flipped on their backs, all traits commonly associated with sentience and consciousness. The cnidarians and ctenophores, on the other hand, have climbed over to the next branch, privileged with a fully functional nervous system. These are those who can respond to stimuli intelligently, showcasing a suite of complex behaviours, from actively seeking prey to seeking out mates. But to be clear, these creatures are still not yet considered sentient, failing as they are in the centralised network of the brain. The cnidarians, known to us as the jellyfish, the sea anemones and the corals, host a more dispersed neural network, sometimes called a neural net, that reaches from mouth to tentacle. But here on up in the cognitive chain, regardless of whether you are 1 and a bit nanograms of tardigrade or 6,000 kilograms of African elephant, the structures of neurons and neurotransmitters remain vastly the same. The only exception to this rule is the ctenophores. The ctenophores are essential to our story, not because they are the next evolutionary step in this long line towards sapience, but because they offer a counterpoint. Recent advancements in genome sequencing have led to some startling new evidence, which, though still highly debated, supports a theory that contradicts the common belief that Porifera and the placozoans were the most basal species of the Animalia branch. Ctenophores are jellyfish-like creatures that move through the water by beating rows of iridescent cilia, and who, in an equally complex manner as the jellyfish, hunt down their prey with retractable sticky tentacles. However, due to the fascinating work done by neuroscientist Leonid Moros, the ctenophores have presented themselves as a unique branch of the Animalia family. Unlike all animals on Earth, the ctenophore's nervous system is built upon an entirely unique scaffolding of genes. Those neurotransmitters usually responsible for sending information about the nervous system, such as dopamine, serotonin, nitric oxide, noradrenaline, acetylcholine, and others, are simply not present in the systems of the ctenophores. And yet, complex behaviour still persists. And not only would this suggest that the separation of their lineage predates the sponges, but more radical is that our conscious conjuring protagonist, the nervous system, has emerged twice in Earth's history along 2 completely independent branches of life. If this is true, it dramatically opens up a potential diversity for complex neural structures, and thus the potential for alien notions of consciousness. But again, how does any of this influence our search for the universal boundaries of consciousness? An interesting component of the evolutionary arms race is that, regardless of the evolutionary branch, each emerging sense always came into existence as a more sophisticated version of touch. Sight, for example, only appeared once the cells could pass on the touch of electromagnetic radiation hitting the skin. Smell was simply the touch of microscopic particles floating in the environment. And of course, hearing is the touch of environmental pressure waves. In its later, more complex manifestation, touch could be responsible for the opening of a mouth when encountering food, or even just the reactionary kick away from an unexpected obstacle. But in its simplest stages, touch was responsible for no less than the separation of body and environment. Taking the story back towards the era of first life. Though an individual cell may have been entirely non-sentient, and thus entirely unaware of its surroundings, it was nonetheless chemically aware of its own inner and outer structure. By this I mean that by hosting a cell wall, it, as a system, could be chemically agitated by any change to its internal biochemistry. When either the outer wall or the inner organelles were somehow interrupted, a chemical necessity for balance would ensure that the cell as a system would react and, in doing so, enhance its chance for survival. Though it didn't so much decide to push towards a more sustainable equilibrium, it did, as a system, respond to its situation. And it was these same simple responses to interaction that eventually gave rise to the many varieties of touch that we know today. Thus, according to this theory, without interaction, awareness is impossible. But as already discussed, neither the cell, the nervous system, or the physical body are things of substance. Rather, these bodies and their characteristics are only abstractions of pattern. So long as complexity provides for a more ultimate functionality, an independent structure of relationships can transcend the nature of any individual. For example, cells. These may remain the same as they always had been, but with the evolution of their collective relationships, they now can operate as a nervous system. Be it a cell, a molecule, a nervous system, a characteristic, a species, or any other form of identifiable nature, nouns never signify things that exist in and of themselves, only systems of relationships built upon broader relationships. So interaction as a phenomenon is not just a matter of things bumping into things. Rather, interaction itself is merely another system of relating relations. But the reason why I remind us all of this here is that we should take note that without this abstraction of unity, i.e. bodies, touch could not have been evoked. And as just suggested, without interaction, awareness is impossible. Now, this is an idea that we shall need to unfold in more detail across later chapters, because metaphysically, it's already quite a hefty claim. Awareness requires interaction. But it also sheds light on the nature of interaction itself, since the process of interaction seems to be no different for physical bodies than it does for more abstract structures like behaviours, tendencies, or characteristics. As a nervous system can emerge from the relations held between cells, behaviours and characteristics can emerge from the relations between a nervous system and its environment. Relationships begat relationships. And considering that the neurobiologist has claimed that this process is precisely that which has enabled the universe to turn on consciousness, it should now be clear why seeking a primordial transition should prove crucial to any definition of consciousness. But for now, I see two essential takeaways regarding the evolution of the nervous system and the hierarchical notion that it implies. These we shall discuss over the coming chapters, but the first we shall discuss is that the nervous system is not by any stretch, a reliably consistent structure. Good morrow, beautiful people. Thank you again for tuning in, for being a part of this. If you aren't already aware, The Infinite Now is an ongoing narrative. Every single month I put up a new chapter, and the chapter follows from the prior, and we're unfolding a story. We're trying to get to some sort of climax, some sort of ending, unfolding the nature of infinity, trying to understand the metaphysics of what reality is, because that's why we're here. So yeah, go back, have a look at those chapters. It will help you understand some of the things that we've spoken about in today's chapter. Obviously, the one just prior to this one will be the most relevant to the one that we just heard. But there was also one called The Digital and the Spaces Between that happened towards the end of last year that would be very helpful to understand some of those last ideas that we unfolded here in this chapter. Apart from that, just wonderful to have your company. Letting you know there's an Instagram if you want to go follow that. Otherwise, do your thing. Much love, and I hope you all have a wonderful, wonderful week. See you later.